All right, everybody, welcome to the video here for lesson number 9. I know with some of my classes I might have gotten to the lesson. Some of them you're doing this on your own. So if you don't need the actual lesson, just fast forward to where you see the homework start. All right, or if you want to just revisit some of the things we went over in class, we could do that together here now. So the opening exercise is just a review of something that we learned in lesson number 8. So in lesson number 8, there were two equations that we learned about. So we learned about the annual interest equation, which is the future value is equal to the principal value times 1 plus the annual rate all to the t for the number of years. And then we also talked about the future value when the interest is compounded more than one time a year. So we have this other formula where n represents the number of times that we're compounding per year. Now, in yesterday or lesson 8's homework assignment, we were able to use that formula to go through and figure out what the effective rate is versus the nominal rate. We're going to revisit that a little bit in today's lesson as well. So for the opening exercise, it tells us that we are compounding monthly. So we're going to use that second future value equation. So I'm going to say the future value of this account is equal to the initial amount of the value of the account, the principal, 1 plus the nominal interest rate, so that's the interest rate for the year, divided by 12, since there are 12 months in a year. And the exponent's going to be 12 months times the number of years. Then it just becomes a calculator problem. If you're having trouble typing this actually into your calculator, you might want to simplify what's in the parentheses first. There's a lot of different ways of doing it. Let me just plug this in here for a second. So we have 0.025. I'm not going to keep flipping back and forth between screens here unless we need to show you something in the calculator. I'm assuming you all can type stuff into the calculator. So we have a value here of 1731.63 money, so we round to 2 decimal places. Now, the first thing that we're going to do in this lesson is we're going to find out about this new number. Right? So to find out about this new number, we can start to look at what happens if we continuously increase our value, right? So in this equation that we just used here, this future value equation, if we make the principal 1, the rate 1, and the time 1, what happens to n, right? Is n increasing? Is it decreasing? What's the deal with n, right? So if we rewrite this future value equation with 1s in for those three things, we get this equation, right? The exponent's 1 times n, so we'll just put n. Now, if n is increasing over time, what happens? So let me just graph that for you. So let me go to Desmos here. So if I graph y equals 1 times 1 plus 1 divided by x, we'll use x instead of n, all to the nth power or x power, we get this function. Now, I don't care about the function over here because that's talking about negative compounding. I don't want a negative compound. I just care about the function as we are increasing over time from 0. So from 0, this function is going up. Now, in your calculator, if you look at the table of values, you'll notice that this function is getting really, really close to 2.7-ish. Right? It's never going to go past 2.7, and we can see as I scroll here, it's staying right in between 2 and 3. Right? So what's happening to my function, right? So as the n value increases, the f value, so we could say as n increases to infinity, the function value is increasing towards 2.7-ish. Well, since it's a special number, it's increasing towards that value, we have a value that we can use for that, or a symbol that we can use to represent that number, just like pi, right? Mathematicians are kind of, lazy at times, so I don't want to write out the decimal pi when I could just use a symbol to represent it. Well, this number comes up a lot also in exponential models, because this is us showing the continuous nature of the function. It's going up forever, right? So sometimes we have things that are interest that is going up or that's being added to our account continuously. So because of that, we have this number. So what f is really approaching, right, the f value is really approaching this number called e. Now, E is actually a button on your calculator, which I'm hoping you can find. E is approximately 2.718 dot, dot, dot. right? It's an irrational number. It goes on forever. There's no repeating in it. And we can start to see that it comes up a lot in our functions, right? It's just a number. It's not a variable, okay? So that means we have a new formula. Our third and last formula we really have to memorize here for this unit. So we can say the future value of an account that's compounded continuously is equal to the principal value times e to the RT. All I'm doing to create this equation is I'm changing this function that we already learned about here, and I'm changing what's inside here to just represent e, because that's what we proved by graphing it. Now, fortunately, you don't ever have to do this part again where we're showing all that. It's just good to know where e comes from. Now we just have to know, how do I use this function, right? So let's use this function, which I'm going to call the PERT equation, P-E-R-T. That's an easy way to remember it. So we'd use this as soon as we see the word continuously. So in number 2, it says Matt has $1,200. He invests using a nominal interest rate of 7.3% compounded continuously. So our interest rate is in our formula, our principal value is in our formula, and this number e is in our formula. So I'm just going to plug all that stuff in with t as my years. That's it. Now, if we want to determine how much money Matt has after 10 years, we can say A of 10 is equal to 1,200 e to the 0.073 times 10. Now, on your calculator, the E button is next to the number 4. You'll notice it's an ln button. So if we hit second ln, the E button will pop up, and it'll even have a nice little exponent for us, right? And if you plug this in, we're going to get a value of $2,490.10. Now it says to determine the effective rate for this account. Now this is something we talked about in the lesson 8's homework, right? The effective rate is the actual percentage that we're including into this account. Now this is taken in consideration. Yes, it's 7.3% compounded over the course of a year, but since it's continuously compounding, every single time I compound, I'm actually adding more to my principal value that we're getting percentages on. So the percent over the year, the actual percent over the course of the year, is going to be slightly more than 7.3%. So how do we determine the effective rate? Well, we have to use our exponent rules. So I'm going to start with the actual function a of t. It's 1,200, that's not going to change, e to the 0.073t. And I'm going to rewrite it using my exponent rule so that the exponent is just t. So now I'm representing the exponent as just years. So I'm changing the exponential model so that it's being compounded over the course of years instead of compounding the interest as well. Now I just have to figure out, well, what the heck is this number? Right, so if I type that into my calculator, e to the 0.073, we get a value here of a of t, which is 1,200 times 1.0757, right? 4 decimal places is usually plenty. And we remember from our functions that we learned in the previous unit, this part of the equation represents 1 plus the rate. Well, if I just want to know the rate, I want to subtract 1 from that number. So if I do 1.0757 minus 1, I get 0.0757. So this is what we call the effective rate. And I'll show it as a percent, move the decimal place 2 times, and we get 7.57%. Super close to what we started with, right? We started with, what was it, 7.3%, but you notice it's a little bit more because not only are we compounding the principal value over the course of the year continuously, we're also compounding the previous interest that was used, right? Number three is just us using this new PERT formula we're learning in this lesson. So if I take my future value is equal to 500 times E to the 0.05 times 14. I'm just plugging in what I know. All right. The nice thing about this chapter is we rarely have an exponent that's a variable. That's more for the next chapter. So these are kind of easy to plug in. So we get $1,006.88. All right, keep going here. So now we have this bank account question. So in class, my plan here was to have you all do this in like little groups of 3. We might not have had time to do that. If we did, awesome. If not, no big deal. We could just do it here. So we have a bank account, and we are investing $10,000. There are 3 different plans we can use. One that compounds the rate once a year, one that compounds quarterly, and one that compounds continuously. Now, if all of these were the same percentage rate, continuously would be the best plan to choose. But notice they all have slightly different rates. So because the continuous rate is the lowest, it might not be the best option for us to choose. So we have to go through and kind of do some math here and see what we got. So for plan A, which I'll call A of T, I'm starting with $10,000, right? So my principal value is 10,000. And I'm saying 1 plus 0.027, that's the rate. That 2 looks like a Z. And that's all to the number of years T. Notice it doesn't tell me how many years, so we're going to have to kind of make an educated guess or use our calculators here to see what we got. Plan B, which we'll call B of T, right, is interest quarterly. So it's still going to be a $10,000 startup or principal value, 1 plus the rate. Now this rate's a little bit different. Quarterly is 4 times a year, so I'll make that 4 to the T. And then C of T is equal to 10,000. Now notice it says continuously, so I'm using the PERT formula. So I have E, and then we have 0.0265 T. Now the easiest way to do this problem and figure out which plan to choose would be to graph all 3 of them. So if you graph all 3 of them and then go into your table of values, you'll actually notice that A of T generates the most money consistently throughout the life of this loan or this investment, right? So A of T generates the most value, right? So as we go up, we're seeing that it's generating the most money. Now we can further prove this by picking an actual number, right? So it says after 8 years, how much money is in each account? So I want to figure out, well, how much money is in each account after 8 years? Now, since you plugged all these in a calculator, if you just look at your table of values, you can figure that out relatively quickly. So as you can see, I have all 3 values now written down. You get them right in your calculators, and we can see again, just to further prove, account A is the best. All right, so let's move on to the homework now. All right, so in the homework, again, we're just kind of practicing this skill. So Dan is investing $750 where we're compounding 5.2% continuously. So again, we're talking about something that's going continuously. So we need that PERT formula. So it says write a function for f of t. So f of t is equal to his original 750 e to the 0.052 t. And then how much money does he have after 9 years? So I'm going to say, well, what is the function's value at 9? So I could say 750 e to the 0.052 times 9. Plug that into my calculator and see what we get. Again, we're talking about money here, so we want to round out 2 decimal places. All right. I promise in the next lesson we won't only talk about money. We'll talk about other stuff. I know you're starting to get bored of money. Right. So we have 1197.60. Then it says, using your calculator, approximate how many years it takes for him to double his investment. Now, this goes all the way back to a previous lesson we did where we were trying to solve equations. The equation we're trying to solve is going to be 750 times 2, which is 1,500, is equal to 750 e to the 0.052x. I want to know x. So in our calculator, if I graph 1,500, make that y sub 1, and make this y sub 2, and see where they intersect, we wind up knowing how many years it takes for him to double his investment. So take a minute and go through and plug that in your calculator here. I'm going to just pause so I can set it all up so you can see it better. All right, so I have here on Desmos the graph. So I've changed my scale so that I could see the whole function and how long it takes. It looks like it's somewhere between 10 and 15 years, right? I changed my Y scale so that I could definitely see the doubling effect happen. And on Desmos, it's really easy. I could just hover over this point and I see how many years it takes. On your calculator, you have to use the intersect button to get there, right? So it takes 13.3 years. So going back to my lesson, it says, you know, how many years does it take to double his investment? Well, 13.3 rounds to 13, but at 13 years, he wouldn't have ever doubled his investment. So we're going to say it takes 14 years for his investment to double, right? Because it was 13.3 on our calculator. The next part says to determine the effective annual rate for the account. So my account here, which we called f of t, I can write as 750 and e to the 0.052, all to the t power. So I'm making it so that the e to the 0.052 is by itself and the exponent is just t. Now, if I evaluate e to the 0.052, I'm going to get a decimal. So I can say f of t is equal to 750 times 1.053 all to the t. And again, just like we did in the lesson, this, remember, represents 1 plus the rate. So if I subtract 1 from that value, the rate, the effective rate in this case, is 0.0534, or about 5.34%. Doesn't say what to round to, so we'll just go out a couple values. Number 2 says, explain how we developed number E. So in class, one of the first things that we did was we took the formula that we learned in lesson number 8, and we replaced ones throughout the whole thing to make it so that n was the only variable. By making n the only variable, we're able to see what happens as n increases continuously. So as n increases continuously, we get really, really close to this number E, right, which we developed the idea of from right on our calculator, right? Now, there are other ways of finding E, but that's how we're going to show it because we're talking about exponents and it becomes an exponential model. Instead of me writing all that down, you could just rewind it if you missed something I said. And that's it. That's your homework. Hopefully that helped. Hopefully the video helped for those of you that weren't here for the lesson, and we can keep going as we move forward throughout this chapter. All right, good luck with everything. See you guys tomorrow.